Swayam Prabha. Digital India. Educated India.
Lesson 2.6 Intersection Control and Signalization. In fact, this is the last lesson under module 2 Traffic Engineering. After completing this lesson, the student will be able to understand the hierarchy of intersection control, understand basic principles of intersection signalization. There are several aspects, several key issues, at least the elementary issues and the principles we will discuss. So, the student will be able to understand those basic principles. The student will be able to design isolated fixed time signals using Webster method. It is one of the approaches for signal time designs. So, that approach we will discuss. So, student will be able to discuss design isolated fixed time signals using Webster method. First thing, what is intersection? All of you know that in a given road network, you will have mid block section and the intersection block. That means, intersection is simply where two or more roads are meeting at a point or at an area. So, intersection is an area where two or more highways join and cross. There are basic two types of intersection what are used normally. One we call at grade intersection, that means all roads are meeting at the same level. So, either all movements are using some common areas of intersection. So, these are roads which are meeting at grade or at the same level, whereas in grade separated intersection, it is or it permits crossing maneuvers at different levels. So, those are grade separated intersections. Obviously, grade separated intersections are better, but most of the cases whatever you find, they are basically at grade intersections, because grade separated intersections are capital intensive structures, capital intensive projects. So, unless and until the traffic or the delay or the chaos in the intersection is really to that level, we normally do not go for grade separated intersection. So, mostly whatever intersections we find in general, they are at grade intersections where all roads join or cross at the same level. So, our focus or our discussion today is basically related to at grade intersection. Now, efficiency, safety, speed and capacity of road system vary very much depend on the type of intersection and design. There are different types of at grade intersection, then you have grade separated intersection. So, what will be the efficiency, what will be the level of safety, what will be the speed and capacity of road system, all those will depend on the type of intersection and what kind of design is adopted for that. An important concept in related to intersection operation is the concept of conflict. traffic movements at intersection involve a number of points or conflict. Those conflict points we normally classify under major conflict and minor conflicts. Crossing conflicts are normally considered as major conflicts. There are merging and diverging conflicts which are also possible. So, those are normally called as minor conflicts. So, suppose a vehicle is going like this, another is coming like this. So, this is essentially a conflict point which is crossing conflict and will come as major conflict. Similarly, two vehicles are coming and they are using the same road. So, here that conflict is merging conflict. Similarly, from a road maybe traffic is taking left, some traffic is taking right. So, this conflict is actually a diverging conflict. So, merging and diverging conflicts are considered as minor conflicts because they are relatively less critical. Crossing conflicts are most severe and therefore, we call crossing conflicts at major conflicts. Obviously, reduction in number of conflict means safer and efficient operation. So, if by any means or by any measure, if we can reduce the number of conflicts, then we can say we are going for safer and efficient traffic operations at intersections. Now, to explain this part further, let us consider two roads which are meeting at an intersection. So, there are four approaches essentially, and if we consider all three approaches, all three movements are allowed from each approach. That means, left turning, right turning and straight going vehicles are allowed. Then from each approach there are three possible movements. So, there are four approaches. So, there are 12 legalized vehicle movements. I am using the word legalized because I am assuming that all movements are allowed. So, if you have a position like that, then you can calculate based on this concept of crossing conflicts, merging conflicts and diverging conflicts. You can calculate there will be 16 major conflicts and 8 minor conflicts. So, altogether 24 conflicts in that intersection area. Now, often the job of traffic engineer is basically to reduce the conflicts to make the operation safer and efficient. This can be done also by making two-way roads as one-way road. Suppose the example what we have discussed, there are two roads, both cases two-way movements are there. Now, if one is made one way, then you can again calculate, you will find the number of conflicts will come down to 11 from 24, and out of those 11, 7 will be major conflicts and 4 will be minor conflicts. And that is the reason you will see that making one way, it means not that every cases or every situations will be able to make roads as one way traffic operation, but making roads one way is also used as a tool for improving the efficiency and safety of traffic operations at signals or intersections, not at signals, at intersections. Now, suppose continuation to this one, suppose if we make both roads one way, then there will be further reductions in number of conflicts, and you will find that there will be only 6 conflicts, out of which 4 will be major and 2 will be minor. Now, this is a typical example of 4 approach intersection with two-way traffic movement on both roads, one-way traffic movement on one road, one-way traffic movement on both roads. We have seen how the conflict points are reduced. If there are pedestrian movements, then pedestrians are trying to cross, vehicle is also coming. So, again this will also generate additional conflicts. So, pedestrians add additional potential conflicts. So, the critical task of traffic engineer is basically to control and manage these conflicts in a manner that ensures safety, that is the most important keyword, and provides efficient movement through the intersection for both motorists and pedestrians. So, traffic engineers focus is not only on motorized vehicle or motorized cars or buses or other vehicle types, but also pedestrians are essential elements and in the overall traffic engineering concepts. So, task is basically to manage these conflicts to ensure efficient and safe operations of traffic as well as pedestrians. With this background, you know that intersection area is basically a very complex situation where you have vehicle movements, different types of vehicle movement, different legalized movement, they are creating conflicts. Also the pedestrians, once pedestrians are there, pedestrian movements are taking place, they add to the number of conflicts. So, it is altogether a complex task, but the complexity varies from one situation to another situation. So, from your experience you can find not that all intersections are equally critical. Some of them may appear to you all right, some places you may find this overall traffic operation is really chaotic and unsafe for maybe both pedestrians and vehicular traffic. So, we need to understand the hierarchy of intersection control just as a concept. There are three basic levels of control that may be implemented at an intersection: level 1, level 2 and level 3. This goes in this order, like in a most simple form, maybe level 1 is okay. Situation becomes a little bit more complex, you go for level 2, further complex operations go for level 3, and then even if it does not bring down the chaos to a desired or to the limiting level, you may have to think of grade separated intersection. Level 1 is based on basic rules of road. That means we don't impose anything on vehicular movement. We don't stop vehicle either by sign or by signal, giving red signal or giving the stop sign or giving any kind of other devices. What we expect that the system will operate based on basic rules of the road. Now, what are the basic rules? When the licenses are given to drivers, they are supposed to know what are the basic rules. So, they are supposed to qualify based on their knowledge and then get the rules. So, every state or district or country, they have their own set of rules, driving rules. So, it is expected that vehicular traffic or the drivers will know the rules, they will follow the rules. Pedestrians also, they know how to cross and they will cross as per the rules and regulations. So, it is essentially the basic or the fundamental rules of the road that if everybody follows, I think the operation is fine under certain situation, right. So, level 1 is we do not impose anything, no traffic signal, no sign. Sign may be there to show that you are approaching an intersection. Okay. So, that kind of sign is fine. Okay. Informatory signs or warning signs are fine, that there are it does not really mean any imposition. So, still it is we can consider that it is operating under basic rules of the road. But some cases you may find that it is left to the judgment and the basic rules. So, a vehicle is coming from the right or vehicle is coming from the left, whether to cross, whether to march, that will drivers will be able to apply judgment, and he will have the ability, and the situation or the context also will help him to make a proper decision. So, when the traffic volume is more, when the situation becomes more complex, probably you cannot just leave it to the basic rules of the route. So, the next stage, once you find that level 1 is not adequate, you go for level 2, that is direct assignment of right of way using yield or stop signs. You may be familiar with yield or stop signs. Stop signs means maybe a vehicle approaching from a minor road. If there is a stop sign, the vehicle has to stop, then look for a gap, and then march or take a turn to the main traffic streams. Yield sign is also another form of control, where we expect minor street vehicles to give priority to the major street traffic. So, he may have to stop or he may not stop depending on the situation. So, if he finds there is no road on no traffic on the major road, he can straightway go and take a turn. But if he finds there is a vehicle which is coming along the major road, he has to then stop, he has to wait, okay, and till he finds a suitable gap. That means, priority of movement is more for major street traffic movement, and priority is less for minor street traffic movement. Now, you may find that still this is also not working. So, suppose you have done that, but as again the traffic volume grows, okay, the complexity grows, more pedestrians are there, more traffic are there, you may find still the stop sign also may not adequate, or yield sign may not adequate. So, then this is level 3, where we go for traffic signalization. That means, you install traffic signal, you share the times for certain movements. Maybe major road movement is taking place, that time you stop minor road traffic, or maybe both roads may be of equal priority. So, one road you stop, you allow other movements, you now stop the other road, allow the movement on the first road. So, like that, traffic signalization, you are essentially the same space, same intersection area can be used for certain type of movements at certain time. So, certain types of movements at certain times, not that all movements take place at the same time. Some movements take place at some time, some other movement takes place at some other time. So, that is the signalization. So, first in a simple form we may try with level 1, it may be okay. As you find level 1 is not adequate, you go for level 2. If you find still level 2 is not adequate, you go for level 3. Further, even the signal, there are a lot of procedures, different types of signal operation is possible, signal isolated signal design individual signals like that, and then it is possible you try to coordinate signal. It is really a vast topic area, there are a lot of procedures, a lot of things to understand. And then if you find still with signal and all sorts of things, you are still not able to manage traffic or ensure adequate safety and efficiency, then one has to think for grade separated intersection. But as I told, our main focus for today's discussion is essentially at grade intersections. And further we will go to this part, traffic signalization. Now, you have level 1, level 2, level 3. The selection of level of control depends on which and how many conflicts a driver should be able to perceive and avoid through the exercise of judgment. So, I told carefully observe this part. What type of conflicts? What type of conflicts and how many conflicts? Both are important. As I told, there are major conflicts, there are minor conflicts. Okay. So, what are the types of conflicts and how many conflicts you expect the driver to perceive and then avoid without making a crash, without making an accident. The driver should be able to avoid through the exercise of judgment. Now, if you find both the type and number are good enough, okay, much lower, lesser, okay, and they do not impose essentially that level of safety problem, then you may happy with level 1, otherwise you go for level 2. Still you are not happy, you find still then your situation is not under control, go for level 3. Now, where it is not reasonable due to the complexity of the situation and operation to expect a driver to perceive and avoid potential conflict, traffic control must be imposed. Control means control by putting maybe stop sign, yield sign, or further by putting traffic signals. There are two factors which primarily affect a driver's ability to avoid conflicts. One, the driver must be able to see a potentially conflicting object to implement an avoidance maneuver. This essentially means basically the geometric design of the intersection. A driver approaching from one approach, first thing he should be able to see that there is another vehicle which is coming from the other approach. So, intersection side distance is the distance required to ensure safe operation of traffic at an intersection. You should be able to see. So, like this is an intersection. So, a vehicle is going from this direction, another vehicle is coming from this direction. So, suppose if this vehicle requires at least this much distance to stop and this vehicle requires again this much distance to stop. So, then this area should be free from obstruction, because this is the line of sight in that way. We will have further discussion under geometric design part about this intersection side distance. So, this is essentially pointing out to the need for adequate intersection side distance. So, first of all, the driver must be able to see a potentially conflicting thing. If he cannot see, if that there are tall building or high rise structure just near the intersection, then unless you reach to the middle of the intersection, you do not see, you cannot see a vehicle which is coming from other sides, other approaches. Second, you may be able to see, but the volume levels that exist must present reasonable opportunities for a safe maneuver. So, this is another aspect what we are trying to point out. What does it mean? It means maybe you are able to see. So, you have adequate side distance, say a vehicle is coming from the minor road. So, the driver is able to see, but he has to get an opportunity to really cross or march to the main traffic stream. He waits, but he does not find any gap, because the volume is so heavy, he keeps waiting for a much longer time. Then again he is not able to perform the maneuver what he intends to do. So, in that case the volume level is critical. If your volume level is beyond certain value, all the approach volumes for different roads, then the driver may not get reasonable opportunities for a safe maneuver. So, looking at the side distance and looking at the overall traffic volume that the intersections are given, both these factors affect driver's ability to avoid conflict. Because if there is a reasonable gap, the traffic volume is not that heavy, driver may keep patience to wait for a suitable thing. Otherwise, he may try to take risk that even a limited opportunity he may try to merge it with the traffic stream or enter into the traffic stream. So, that may cause potential safety problem. Traffic signal alternatively assigns right of way to specific movements, as I indicated. Some movements are allowed at some time, other movements are stopped. Then the movements which were allowed earlier will be stopped and other movements will be allowed. So, therefore, it is expected to reduce the number and severity of conflicts. Both the number and the severity are expected to get reduced. There is certain advantages of traffic signal control. Maybe they are obvious based on our earlier discussion, but I will just try to make certain points. Traffic signal provide orderly movement of traffic. the chaos is eliminated, because some movements are allowed at some time, some other movements are allowed some other time, not all movements are taking place at the same time. So, it provides orderly movement, increase traffic handling capacity of intersection. Obviously, for that it is necessary to review signal timings frequently. This part is very important. Not only this part, it is also necessary to ensure that the geometric design of intersection is proper. That is another key aspect. Once the geometric design part is ensured, that you have adequate and efficient design standard, then also if you just design signal once and leave it, that may not give required efficiency, because over a period of time the overall traffic volume may change, the traffic volume from different approaches may change. So, you need to, most of the cases these are applicable for fixed time signal or pre-timed signals, which are very common in most of the cases. Most of the situations you will find they are essentially pre-timed fixed signals. So, it is necessary to update the signal timings, because what you will do today may be based on today's traffic conditions. So, after 1 year or 1.5 year, the traffic volume, overall traffic volume may change, the approach volumes from different approaches may change. So, it is necessary to review it time to time. If you do that, obviously you may provide or the best traffic handling capacity. Signals reduce the frequency and severity of certain types of crashes, especially the right angle collision, because the movements are shared over time. Signals may be coordinated to provide continuous and nearly continuous movement at a definite speed along a route under favorable condition. Carefully observe this part, under favorable condition. Not always, there are a lot of complexities, lot of aspects which are to be taken into consideration. Then it is possible that you give smooth traffic movement along the major traffic flow, directions of major traffic flow, by coordinating a number of signals along that route. So, the priority you can decide, the movements can be much better, the flow can be much better, travel speed may be higher, but under favorable conditions. There are so many aspects. It is conceptually sounds, but if you try to implement it, there are a lot of issues which comes under advanced part of the discussion or advanced traffic engineering component. Signals may be used to interrupt heavy traffic volumes, heavy traffic at intervals to permit other traffic, both vehicular and pedestrians, again both are important, to cross. In some cases you may find that heavy traffics are moving and it is not safe for the smaller vehicles or even pedestrians to cross. So, you just intermittently you stop those heavy traffics to make sure that other vehicles or pedestrians can move or can cross efficiently and safely. There are certain disadvantages also along associated with traffic signal coordination. As I indicated, if you do not update the signal timings for fixed time or pre-timed signal, then the delay may be even more. Some cases, because you are providing signals, people may try to avoid routes which are having signals. So, they may take a different route. So, the route distribution may change. Okay. So, it is necessary to maintain the signals, to ensure that you update the signal timings at regular interval and look at the other aspects. Now, coming to principles of intersection signalization. First thing is basically your decision to install traffic signal, it depends on a large number of factors, and it is again a complex task also, because combinations of traffic volume, potential conflicts, both nature and number of conflicts, what is the present overall safety of operation, what is the present efficiency of operation, what is the level of driver's convenience or inconvenience, all these combinedly will decide whether you need to go for signalization. There are certain warrants also. Different countries, different states or different local bodies may have their own warrants, that under which condition a traffic signal is really acceptable. So, but it is most of the cases the values may change, the levels may change, but it is generally combinations of traffic volume, potential conflicts, overall safety of operation, efficiency of operation and driver's convenience. All these things are important. Now, we try to understand the principles of intersection signalization, but we will learn it. There are a lot of terms and definitions which must be known to you very clearly. So, we try to develop an understanding about those terms and definitions, and through that we will try to develop our understanding or try to know the basic principles for signalization. First thing is components related to signal cycle, that is the thing, components related to signal cycle. First thing, what is cycle? A signal cycle is one complete rotation through all the indications provided. You all are familiar with traffic signals. So, if you are moving, sometimes you may get red, amber, sometimes green. So, a complete rotation through all the indications is provided by a signal cycle. Then cycle length. Cycle length is the time to complete one full cycle of indications, one full cycle of indications. So, what is the time required for providing one full cycle of indication? That is essentially cycle length. Then the concept of interval, it is very important. What is interval? The interval is a period of time during which no signal indication changes. That means, when you are operating, suppose it is red, as long as it remains red, it is an interval. That means, it does not change, it does not change from red to amber or green to amber or green to red or red to green, it does not change. So, the interval is a period of time during which no signal indication changes. There are different types of interval. One is change interval. What is change interval? Normally, yellow indication forming part of the transition from green to red, in which movements about to lose green are given a yellow signal, while all other movements have a red signal. That interval we call as change interval. Let me try to explain it further. Suppose the green is given, so vehicles are allowed to move freely. Now, suddenly if you give red, it is difficult to vehicle to stop, because the signal indication changes abruptly. So, you provide yellow indication in between green and red indications, yellow or amber. So, that indications forming a transition from green to red, in which movements about to lose green, that means earlier it was green, now it is amber, so or yellow. So, movements about to lose green are given a yellow signal, and all other movements still have red signal. When a particular movement under consideration, when it was green, then also all other movements were red, given red signals. When this movement is given under consideration is given amber or yellow signal, still all other movements are given red signal. Red signal is essentially continued. So, that yellow indication, that interval we call change interval. Then clearance interval. Clearance interval is also part of transition from green to red for a set of movement when all movements have a red signal. It is essentially indicating all red kind of situation. So, all movements have a red signal because you suppose in amber also some vehicles will move. Now, those vehicles should be able to cross the intersection safely before another movement is allowed or vehicles are allowed from other approaches, right, because otherwise still there may be safety problem. So, this is the clearance interval. Then the green interval. Green interval, for each movement at least there is one green interval during the signal cycle, because signal cycle gives movement, all movements are allowed at least for some time during a signal cycle. So, each movement has one green interval during the signal cycle. During this interval, the movements permitted have a green light. So, only the movements which are permitted will have green light, while all other movements have a red light. So, which are the movements you are allowing, that should have green light, all other movements will have red light. Similarly, red interval, each movement has a red interval during the signal cycle, like during a signal cycle each movement will get green interval, each movement will also get red interval. So, during red interval all movements not permitted have red light. So, they will not be able to move. That is the concept of interval and different types of interval. Now, coming to the concept of phase. A signal phase consists of a green interval plus the change and clearance interval that follow it. Essentially, in a phase we divide the movements. Suppose this is a simple two phase signal, it is also possible to have three phase signal or four phase signal. Let us take an example of a two phase signal. These are the two roads which are meeting. So, obviously, when you are providing signal, you do not allow all movements to take place at the same time. So, given the signal time, you divide the signal time into different phases. Suppose this is a two phase signal, this is phase 1, where you do not allow any movement on east west road. Suppose let me consider this one as the east west road and this is north south road. So, east west road no movement is allowed, only north south roads all movements are allowed. So, you are allowing basically 6 legalized movement. From this approach left, straight, right, from that other side also left, straight and right. Now, this is phase 1. In phase 2, you do not allow movement on north south road, you allow only movement for east west road. So, this road only allowed, movements are allowed. So, here again from each approach you are allowing all 3 movements. So, phase 1 plus phase 2 is one complete cycle. Now, you might be thinking, I am sure, that this here also we are allowing right turning traffic and the straight going traffic is also allowed from that other direction. So, there may be potential conflicts. Yes, in phase 2 operation in this particular example we are allowing that conflicts, but this kind of things or this kind of phase may be still okay if your right turning volume and the straight going volume from the other direction they are not significant. That means, altogether the traffic volume for right turning and the straight going from the opposite direction they are not heavy and suitable gaps may be obtained by the right turning traffic, maybe a few vehicles are there. So, they can still get a gap within that phase to take right turn safely, but as the movement as the traffic volume grows, maybe right turning traffic is also more, straight traffic from the opposite direction this one is also more, same thing is here also. So, then you may have to provide a separate phase. So, we may go for maybe 3 phase signal. Here you can see that in phase 1 again this east west road movement is stopped, all movements are stopped, only north south road we are allowing movement. Here we are allowing left turn and straight, from the opposite direction also we are allowing left turn and straight. So, there is no conflict. This right turn is also stopped, the right turn from the opposite direction is also stopped. So, there is no conflicting movement. This is phase 1. In phase 2, we just clear this 2 right turning movements assuming that north south is the major road and east west is a minor road. We are assuming that east west is a minor road and there is very little right turning traffic. Often it happens like that, that both roads may not have equal priority. So, one may be a major road and another may be a small crossroad. So, major roads, suppose in this example let us consider that north south road is a major road. So, you have lot of right turning traffic. So, we are giving a separate phase, that is phase 2 for right turn. So, this right turn is taking place and this right turn is taking place. So, only right turning vehicles are allowed. So, there is essentially no conflict. In phase 3, we stop movement on north south road. Movements are allowed now on east west road, and like in earlier example, we are allowing now for all the 3 movements, assuming that since it is a minor road, right turning traffic is not significant. So, they can somehow find a gap, suitable gap, and safely do the maneuver. So, this is an example of 3-phase signal. If you find both routes are equally important, then like as I have done for phase 1 and phase 2 for north south traffic, similarly you may need total maybe another 2 phases. So, you may have to design a 4-phase signal for that kind of situation. Coming to the of signal operation, there are 3 types of operation: pre-timed operation, semi-actuated operations and full actuated operations. In pre-timed operation, the cycle length, phase sequence and timings of each interval are constant during that period. So, we do not consider short fluctuation in traffic demand, total and approach volumes. In semi-actuated operations, detectors are placed on minor approaches only. So, semi-actuated operation is suitable when you have a major road and the minor road. So, all the time it will be green generally for the major road movement, and detectors are placed for minor road approaches. If there are actuations are noted from one of the minor approaches, then the traffic signal may turn red for the major road traffic and may become green for the minor road traffic, but they are subject to limitations like how much minimum green time should be given for the major road traffic, what is the maximum green time that may be given for the minor road traffic under all those conditions. And both roads are important, then we may go for full actuated operation, where every lane of every approach must be monitored by a detector, and accordingly the signal cycle, sequence of phase, green time, split, everything may be calculated, and all this may vary from cycle to cycle. Coming to treatment for right turns, we have seen that right turning traffic, they are the problematic one. So, in phase design we have discussed that in one case 2-phase signal design we have allowed right turn when the opposing traffic was there, and in 3-phase design we have not allowed right turn when the straight traffic from opposite direction was allowed. So, basically there are 2 types of treatments. One is permitted right turns, where right turns are made across an opposing flow of vehicles. That means, a situation like this, you have a right turn and also you have vehicles from the opposite direction. So, that is permitted right turn. Protected right turn is made without an opposing vehicular flow. That means, when these right turns are taking place, there is no vehicle from the opposite direction. So, it is a situation like as I have shown it here. This is a protected right turn. Right turn is made, so there is no straight moving vehicle. Coming to the concept of discharge headways, saturation flow, loss times, you are already familiar with the concept. I have discussed earlier in other lessons about the saturation headway, which is constant headway achieved. Saturation flow rate is the flow rate with respect to saturation headway. I have also discussed earlier about the startup loss time and clearance loss time. Starter loss time is the summation of incremental headways above h. Initial few vehicles, for few vehicles this is applicable, they will have longer headways than the saturation headway, and startup loss time occurs every time a sequence of vehicles starts moving on a green signal. So, when the vehicle starts moving on a green signal, every time this queue starts moving, startup loss time will occur. Similarly, the clearance loss time is the time between last vehicles from one approach entering the intersection and the initiation of the green signal for conflicting movements. So, clearance loss time occurs with stopping of queue at the end of green signal. All these concepts I have discussed earlier. So, I am not elaborating them once again. So, the total loss time is clearance loss time, initial basically total loss time is startup loss time plus clearance loss time. So, we denote it as L 1 plus L 2 and normally total loss time is denoted as T L. Now, coming to the effective green time, this is a new concept here. For any given set of movements, effective green time is actually the amount of time vehicles are moving at a rate of one vehicle in every 8 seconds. That means, during the whole period, not that always vehicles are moving with one vehicle in every 8 seconds. That is happening when the headway is operating under saturation headway. But if we take the complete time, then what is the effective green time that we can calculate, where during this complete effective green time we can assume that vehicles are flowing at a rate of one vehicle in every 8 seconds. So, this is normally denoted as small g I. How we can calculate that? This is basically the total green time that is given for a movement I plus yellow and red intervals, all red intervals for that movement, that is y I, minus total time lost, y is y I. So, this is total time lost is nothing but L 1 plus L 2. So, you have basically green time, then amber, then all red. Okay. Now, during this whole time, flow is not taking place at one vehicle in every 8 seconds, it is not taking place in that manner. So, this is the total time green plus yellow plus amber minus this total loss time. So, that is the effective green time, where we can assume that vehicles are moving at a rate of one vehicle in every 8 seconds. Now, capacity of intersection lane or lane group may be calculated now easily. Remember that saturation flow rate represents the capacity of an intersection lane or lane group, assuming that the light is always green, but this is not the case in reality. Light is not always green. So, therefore, the portion of the real time that is effective green is defined by the green ratio. What is green ratio? Green ratio is nothing but the ratio of the effective green time to the total cycle length. So, what we have done, effective green time is defined that amount of equivalent green time where we can assume the flow is taking place with one vehicle per h second, where h is the saturation headway. So, therefore, this is the effective green time to cycle time, that ratio is known as green ratio. So, obviously, with the saturation flow for a given approach or lane group, if we multiply it with by this G by C ratio, that is the green ratio, then we will get the capacity. Let us take a small example. If the cycle length is 60 seconds, green time is 20 seconds, yellow plus all red time may be 3 seconds, saturation headway is estimated as maybe 2.4 seconds, startup loss time is 2 seconds, clearance loss time is 1 second. Then how we can calculate the capacity? First, we will calculate the saturation flow rate, is 3600 seconds in an hour, divided by the saturation headway. So, 1500 vehicles per hour per lane. Then this small g, okay, that is equal to capital G, that is the total green time 20 seconds, plus yellow plus all red time, which is 3 seconds, minus startup loss time minus clearance loss time, or the total loss time. So, therefore, this is totally 3, 2 plus 1. So, it gets 20 seconds, 7 seconds. So, now therefore, the capacity is saturation flow multiply, because saturation flow is applicable for continuous green signal. So, this will be multiplied by G by C ratio, effective green to cycle time ratio. So, 27 by 60 you get 675 vehicles. Coming to the design of isolated fixed time signals, there are a lot of approaches, varieties of approaches are available. Okay, simplest to complicated, it is not possible really to cover all the approaches. So, I will just cover the simplest one, which is used also in many places, that is Webster method. So, essentially using Webster method, we try to find out the optimum cycle time that will minimize the total delay. So, for a wide range of practical conditions, this Webster method is applicable and minimum intersection delay is obtained when the cycle length is given by this formula. So, this is calculated 1.5 L plus 5 by 1 minus sum over y max sum over I equal to 1 to phi. Phi C0 is the optimum cycle length is second, phi is the number of phases, L is the total lost time per cycle, you are aware of this concept. Y max is the critical flow ratio, this is a slightly new concept. It is the maximum value of the ratios of approaches flows to saturation flow for all lane groups using that phase. That means Qij by Sj. Sj is the saturation flow for lane group J, Qij is the flow on lane groups having green signal during phase I. Okay. So, that way we get the critical flow. Once you get the critical flow ratio, you can calculate optimum signal cycle, and once the cycle time is calculated, the other thing, the green times may be calculated. I will just show it with a small and very simple example. Average normal flow of traffic on crossroads A and B during the design periods are 400 and 250 PCU per hour. The saturation flow values for these two roads are maybe 1250 and 1000 PCU per hour. The all red time required for pedestrian is 12 seconds. This is a very simple example, but just to show you the calculations. So, we calculate YA. YA, what is YA? YA, I have told that it is the critical flow ratio. In this case, it is only one value is given. So, QA is YA equal to QA by SA, QA flow is 400, corresponding saturation flow is 1250. So, you get 0.32 as the ratio. Similarly, YB is 0.25 and Y is sum over YA plus YB for 0.5 second, and total lost time is 2n plus R. So, 2 into 2 plus 12 seconds, all red time is 12 seconds and there are 2 lengths. So, there are 16 seconds. Once you calculate that using the given formula, you can calculate the C0 values, which is the total cycle length, which will optimize the total delay, that is 67.5 seconds. Now, green time for approach A will be a ratio of this 0.32 YA by sum over Y, because sum over Y is 0.5 seconds, out of that for approach A it is 0.32. So, 0.32 by 0.5 seconds multiplied by not 67.5, but 67.5 minus 16. Why 16? 16 is kept because all right time is 12 and embed time we are assuming 2 seconds. So, there are 2 phases, so 2 into 2 4 seconds. So, 12 by 4 16. So, 67.5 minus 16, this multiplied by 0.32 by 0.57. So, 29 seconds. Similarly, for approach B, green time is 22.5 seconds. So, that way you can calculate. Of course, this is a very simple example and you need to refer books, other books and other examples to have further understanding about the signal design or cycle design, phase design. This is just an elementary ideas. Some of the questions: define major and minor conflict, define basic levels of control that may be implemented at an intersection, define and discuss types of signal operation, what is the difference between permitted right turns and protected right turns, explain your understanding about effective green time. Now, quickly trying to answer some of the questions. Capacity and level of service, this already I have discussed earlier. As per HCM, the definitions are there. Different traffic factors affecting traffic capacity, primarily percentage of commercial vehicle, that is very important, and the directional distribution. So, these are the two major traffic factors which are affecting capacity. How the free flow speed is estimated from basic free flow speed for freeway and multi-lane highways, the approach is basic free flow speed, and then that is reduced considering the relevant factors. The factors or correction factors for freeways are adjustment for lane width, adjustment for right shoulder lateral clearance, adjustment for number of lanes, and adjustment for interchange density form. While for multi-lane highways, the required adjustments are due to lane width, due to lateral clearance, for median type, and also for access points. What are the MOEs considered while capacity estimating capacity of two-lane highways? You know that there are two types of two-lane highways, class 1 and class 2. For class 1, efficient mobility is paramount. Therefore, LOA's difference in terms of both percentage time spent following and average travel speed. For class 2 highway, mobility is less critical, therefore, LO is different only in terms of percentage of time spent following, without considering or the average travel speed. Now, since this is the last lesson under this module, I am also trying to answer quickly the questions what I raised for this lesson. Major and minor conflicts, you don't know that crossing is the major conflicts, and minor marching and diverging are considered as the minor conflicts. Mention basic levels of control that may be implemented at an intersection. There are 3 levels of control: level 1, level 2, level 3. One is basic rules of the road. Level 2, direct assignment of right of way using yield or stop sign. Level 3 is traffic signalization. Discuss different types of signal operations. We have told that there are 3 types of signal operation: pre-timed operation, which is fixed signal cycle and sequence and time everything. Then semi-actuated operation, one major road, one minor road, there it is more suitable, and then full actuated operations where every lane of every approach must be monitored by detector, and cycle length, sequence of phases, green time, speed, everything may vary. What is the difference between permitted right turns and protected right turns? Permitted right turns, you know that right turns made across an opposing flow of vehicles, protected right turns made without an opposing flow of vehicle. Explain you understand about the effective green time. You know that for any given set of movements, effective green time is the amount of time vehicles are moving at a rate of one vehicle in every h second, where h is the saturation flow. It is the actual green time plus sum of yellow and red intervals minus the total lost time. So, that way you can calculate the effective green time. Thank you.